So our next talk is by Madeleine Kyng, and she'll tell us about computing zeta functions of algebraic curves using Harvey's trace method.
Right, yes. Hi, everyone. I'm Madeleine Kyng. I'm a PhD student from Australia from the University of New South Wales, supervised by David Harvey. I'll be talking to you today about my paper, Computing Zeta Functions of Algebraic Curves using Harvey's trace formula, in which a new algorithm for computing the zeta function of a curve over a finite field was presented. The goal of the paper was a practical algorithm that could take a completely arbitrary curve as input and compute the zeta function. Specifically, we wanted an algorithm that takes as input an absolutely irreducible bivariate polynomial defining a plane curve over a finite field, and outputs the zeta function of the unique non-singular projective curve that is birational to that plane curve. There exist many practical algorithms for computing the zeta function for specific classes of curves, like for elliptic curves, hyperelliptic curves, non-degenerate plane curves, and more. The best known zeta function algorithm has got to be Scope's algorithm for counting points on elliptic curves. Scope's algorithm was the first polynomial time algorithm for this problem of counting points on elliptic curves. It achieves this nice time complexity of soft of log q to the 5 for an input defined over the finite field of cardinality q. And the way it works is by computing the trace of the Frobenius morphism on the curve modulo a lot of small primes L. And you do this for an appropriate set of small primes as dictated by the Hasse-Weil bound for the number of points on the curve. And from that, you recover the actual point count for the curve via the Chinese remainder theorem. Scope's algorithm was generalized within a few years by Keeler and Edelman and Huang to work for curves of arbitrary genus, not just genus 1. And these descendants still have polynomial time complexity when the genus is fixed, but treating the genus as a parameter, these algorithms have horrendous time complexity. It's doubly exponential in the genus, and these scope descendants are impractical for arbitrary curves of genus greater than 2. The strategy that has been most successful for computing zeta functions of curves of higher genus is to compute the action of Frobenius in a p-adic cohomology of the curve to explicitly do that. And this is what Kedlaya did in his 2001 paper for computing zeta functions of hyperelliptic curves. Using Monsky-Washnitzer cohomology, Kedlaya achieved an algorithm for counting points on hyperelliptic curves that achieved this nice time complexity of soft O of g to the 4, and this was vastly more efficient than what had come before him. Kedlaya's approach was generalized within a few years to work for larger classes of curves. It was generalized to superelliptic curves by Gaudry and Gorel, generalized to CAB curves by Denef and Vercauteren, and generalized to non-degenerate plane curves by Kastrick, Denef, and Vercauteren. These descendants of Kedlaya have time complexity polynomial in the genus and quasi-linear in the prime P. More recently, in 2016, Teichmann developed a Kedlaya-style algorithm for computing the zeta function that applies to a fairly general class of curves, including all aforementioned classes of curves. Prior to my paper, this algorithm was definitely the most general practical algorithm for computing zeta functions in higher genus, and this algorithm has been included in Magma since 2017 due to an implementation by Teichmann himself. Teichmann's algorithm applies to any input for which a good lift to characteristic 0 is known, where a good lift is a lift meeting some technical p-adic conditions on the discriminant of that lift. Okay. In practice, Teichmann's algorithm takes as input a prime P and a polynomial F defined over a number field where the prime is inert in that number field and this polynomial F is modic in Y and defines a good lift of its reduction mod P. The algorithm then computes the zeta function in times sextic in the Y degree of the input and quartic in the X degree of the input and is quasi-linear in P. The applicability of Teichmann's algorithm depends on the existence of algorithms that compute this required good lift. There always exists a good lift in characteristic greater than 2, but in some cases it is difficult to compute this good lift. So at present, Teichmann's algorithm is not capable of accepting every possible input bar f over a finite field. More recently, since the publication of Teichmann's paper, there have been efforts to expand the class of curves to which Teichmann is applicable by developing lifting algorithms. In the case of an input bar f that defines a non-singular curve in the toric surface associated with the Newton polygon of the input, a naive Newton polygon preserving lift almost always works. In 2017, at the time Teichmann provided the implementation in Magma, Kastrick and Teichmann had written a paper with lifting procedures developed for curves of genus at most phi. This was included with his implementation in Magma. And more recently, Kastrick and Vermeulen in 2020 published a paper, and along with that paper, some Magma code with procedures for lifting inputs that have y degree at most 5. That is, for lifting inputs with low gonality at most 5. As genus and gonality increase, the lifting problem seemingly becomes more difficult. This is where the new algorithm has the advantage. The new algorithm can accept any input bar f with no complicated lifting procedure needing to be done to pre-process the input. The time complexity of the new algorithm is also similar to those Kedlaya descendants. It's polynomial in the degree d of the input plane curve, though for us, sadly, the exponent on that degree is definitely worse. The new algorithm is based on Harvey's trace formula, and that does not involve any p-adic cohomology like the Kedlaya descendants. So it's fairly easy to understand, and it's fairly easy to implement, and it has been implemented by me in Magma. The main theorem of this talk and the main theorem of my paper is that the new algorithm has the following properties. It takes as input an absolutely irreducible bivariate polynomial defining a plane curve over the finite field of size q. It outputs the zeta function of the unique non-singular projective curve birational to that plane curve, and it does so in time, polynomial in the degree d of the input plane curve, and quasi-linear in the square root of p. Okay. Despite the inferior asymptotic time complexity that I mentioned, there are many examples where the new algorithm outperforms Teichmann's algorithm. Here is one such example. This I haven't provided on the slide the defining equation of, but you can find it on my GitHub. This example has genus 12, is defined over the finite field of cardinality 101, and it has this Newton polygon here with vertices at 0, 0, 35, 0, and 0, 5. This Newton polygon has 66 interior points, but the curve only has genus 12. And what that means is that this input defines a curve that is singular in the toric surface associated with the Newton polygon. And what that means is that a naive Newton polygon preserving lift probably won't be a good lift for Teichmann. However, because the y degree here is 5, that means the methods of Kastrick and Vermeulen from the 2020 paper apply, and we can actually feed this input into Teichmann's algorithm. On a computer with the specs stated on the slide here, I ran my code for the new algorithm, and I ran Teichmann's code for his algorithm plus the lifting code. And over 12 hours, Teichmann's code plus lifting didn't manage to compute the zeta function. I just killed it after 12 hours, but my code took just 2.3 minutes to compute the zeta function of the input. Lifting took a whole 37 minutes in itself for this one. Okay, on this slide, I have an example of an input that, as far as I'm aware, falls outside of the class of inputs that Teichmann can handle. The way this input was selected was by requiring that the genus be at least 9, that the y degree be at least 6, and that the input define a badly singular plane curve with a non-ordinary singularity. The The reason I'm requiring that the genus be at least 9 is that then a general curve of that genus will have gonality at least 6, and that'll be beyond what Kastrick and Vermeulen can deal with from their 2020 lifting procedure paper. On that same computer, it took 10.5 minutes for my code to compute the zeta function of this input. There are 6 more examples just like this, selected in the same way, that appear in my paper. I'd be very interested to know if someone could figure out a way for those 7 examples to compute that good lift for Teichmann and then feed it into Teichmann. Or alternatively, if someone could develop a zeta function algorithm that can handle these curves as general as this zeta function algorithm that can beat the runtimes that are published in my paper. Okay, let's see with what algorithm I achieved this good performance. The new algorithm is composed of 2 sub-algorithms. The first sub-algorithm does the work of counting points on the input plane model using a more efficient version of Harvey's trace formula. The second sub-algorithm does the work of computing the differences in point counts between the input plane model and the unique non-singular projective curve that we are actually trying to compute the zeta function. We count points in sub-algorithm 1 using the theorem that appears before you on this slide here. This is my paper's version of the trace formula. It takes into account the Newton polygon of the input, not just the degree of the input plane curve. For simplicity, I'm only presenting it here for prime fields and where the prime is large enough to get this nicer version of the trace formula. So the formula states that the number of points on the curve cut out by bar F in the 2D affine torus in the degree K extension of the base field is this weighted sum of traces of K powers of these matrices NS mod P to the lambda. To construct these matrices NS that appear in this trace formula, the first thing we need to do is to compute a lift F, a Newton polygon preserving lift F of the input bar F to the p-adic integers. And then this matrix NS is a square matrix of size equal to roughly the volume of the S-fold dilation of the input Newton polygon. And its rows and columns are indexed by monomials of the S-fold dilation of the Newton polygon, where when I say monomials here, I'm identifying the monomial x to the I, y to the j with the 2D lattice point I, j. So the entry in NS at the row indexed by monomial u and the column indexed by monomial v is the coefficient of f to the s to the p minus 1 at monomial p times v minus u. The proof of the trace formula is elementary. What we do is we set up an indicator function whose domain is p to the k minus 1 pairs of p to the k minus 1 roots of unity over the p-adic integers, and whose codomain is the integer 1 p to the lambda. And what this indicator function indicates is whether that pair AB, when you reduce it mod p, is a 0 of f. And then, of course, if you just take the sum of this indicator function over the domain, what you will be counting with that sum, mod p to the lambda, is the number of fp to the k rational points on the curve in the torus. In this nice case we're in here where p is bigger than lambda on k, then taking h equal to 1 minus f to the p to the k minus 1 to the lambda will work as our indicator function. So with this indicator function, we get this first nice formula here, which expresses the number of points in the degree k extension as a sum of sums of coefficients of powers of f to the p to the k minus 1. To get from that first line to that second line, we exploit this map that sends each variable to its p power, and that's how we manage to efficiently compute those coefficients that we need in our sum. With that map, we compute those coefficients by just taking the k power of the matrix and S that I defined on that last slide, and then the coefficients that we actually want in our sum appear on the diagonal of that k power, and that's how we get this trace formula. We get the nice complexity in P, the square root complexity in P, because we only need a small subset of the coefficients of f to the s to the p minus 1 to construct that matrix MS. A straightforward implementation of that trace formula lets us count points on the curve in the first R extensions of the base field mod p to the lambda in this time here. Soft O of R times n squared times p squared times lambda to the 8 times the volume of the Newton polygon cubed, where that n there is log p of the field cardinality cubed. This time complexity stated on the slide here assumes that we are naively computing those matrices ns. This is the time complexity you get by computing the polynomials f to the s to the p minus 1 in their entirety, instead of just getting the coefficients we actually care about. And to get just the coefficients we actually care about more efficiently, we use Harvey's deformation recurrences from his 2015 paper, and that's how the p squared gets down from p squared to p to the half. Okay, now let's talk about sub-algorithm 2. One way we could do the work of sub-algorithm 2 is we could compute the zeta function of the plane model itself, and then we could remove factors from the numerator of that zeta function whose roots have the wrong absolute value, and that would give us the zeta function of the non-singular curve. To compute the zeta function of the plane model, we have to count points in sufficiently many extensions to recover the numerator of that zeta function. We could, for example, always go up to Bombier's bound on the degree of the numerator of the zeta function, but we're going to do a lot better than this. We will compute the corrections much more cheaply. Let me remind you here of the relationship between the non-singular projective curve x tilde and the input curve x. Let Rx be the closure of the input plane curve x in two-dimensional projective space. Then what x tilde is the normalization of the projective plane curve bar x. And we have this normalization morphism pi from x tilde to bar x that restricts to an isomorphism away from the singular points of bar x. So this gives us a way of computing corrections. What we basically want to do to compute the corrections is count the points of that singular subscheme of bar x, and then also count points in the pre-image under the morphism pi of that subscheme. To count points in that pre-image, what we will do is exploit a factorization algorithm. Namely, we will exploit the Monte's algorithm. The Monte's algorithm is an efficient algorithm for computing the factorization of a prime in the ring of integers of a number field, and it's an efficient algorithm for the function field analog of that problem, which is to compute the factorization of an irreducible px in a maximal order of a function field extending the rational function field at qx. And Monte's can do this in time soft of d1 cubed, where d1 here is the y degree of the defining polynomial bar f. This picture shows how this is all going to work. Here are input plane curve x. It's singular. You can see there that there is a singular point, one singular point on the curve. And we can see that in this picture, the non-singular curve above it has 2 points lying over that one singular point. So what we want to do is be able to locate those two points lying over the singular point and count them. The way that we will do this is by first finding the x coordinate of that one singular point on the input plane curve. Let's call that x coordinate x naught. Then what we will do is we will apply the Monte's algorithm to factor the polynomial x minus x naught in the coordinate ring of the normalization of x. The maximal ideal factors that appear in that factorization are exactly the points on the non-singular curve that have that x coordinate. And here in this picture, because in this picture, I'm assuming that the input bar f is monic in y, and because that singular point is the only point on x that has x coordinate x naught, then those 2 points that I found in that factorization, those two maximal ideals, are exactly the 2 points lying over that one singular point. So what we do in general is based on that example. What we do in general is compute 3 subschemes, a subscheme y of the projected line, a subscheme z of the projected plane curve bar x, and a subscheme tilde z of the non-singular projective curve that we are trying to compute the zeta function of. The subscheme y will be a subscheme of bad points on the projective line, and it's going to contain the point at infinity, the zeros of the leading coefficient of bar f when regarded as a univariate polynomial in y, and the x coordinates of singular points of the plane curve x. Then the subscheme z of bar x is going to be defined to contain the points at infinity of the projected plane curve bar x, together with the points on x whose x coordinate belongs to the bad points on the projected line. Then z tilde, a subscheme of the non-singular projected curve x tilde, is going to be defined to be the points in on that non-singular projected curve whose x coordinate belongs to y. And having set everything up this way, what z tilde will be is the pre-image under the normalization morphism pi of z. And so we're actually going to be able to make corrections here. We will make corrections by removing from the point counts that we count using some algorithm 1, the contribution of the subscheme z, and we will add in the contribution of the subscheme z tilde. Everything here, all these subschemes here are going to be easy to compute. The subscheme y of the projected line can be computed by calculating the resultant of the input polynomial bar f with each of its partial derivatives. The subscheme z of bar x can be computed from that set of bad points y. Instead of bad points y, we represent the bad points as irreducibles in the variable x. So the way we compute this subscheme z is by factoring the defining polynomial bar f modulo each of those irreducibles representing the bad points. And then the way the subscheme z tilde is computed is just by applying the Monty's algorithm for each of the bad points. Okay. Now that we know how corrections works, I can tell you how the whole algorithm works. Step 1 of the algorithm is to apply sub-algorithm 1, apply the trace formula to count points on the plane curve in extensions of degree 1 up to the genus. We only ever need to go as far as the degree g extension. We don't need to go up to Bombieri's bound. We never need to go further than the genus. And we count these points to the p-adic precision determined by the passive A bound for the number of points on the non-singular curve in the degree g extension. The next thing to do then is to locate the set of bad points on the projected line for the input plane curve. And as I said, this is just some resultant calculations and it's some GCD calculations. The next thing to do then is to compute the subscheme Z of the projected plane curve. And as we're computing it, we're adjusting the point counts from step 1 to remove the contribution of points on bar x that lie above the bad points on the projected line, and this involves just factorizing polynomials over finite fields. The next step is to compute the subscheme z tilde, and as we're computing it, we're adjusting the point counts from the previous step to add the contribution of points on the non-singular curve that lie above the bad points on the projected line, and this just involves applying Monty's algorithm for each of those bad points. And now at this stage, we would have the point counts for the non-singular projected curve in extensions of degree 1 up to the genus. And by the Bay conjectures, we have symmetry in the coefficients of the numerator of that zeta function. So those G point counts are enough to actually recover the zeta function. And we are done. That's all. Thank you for listening.